Yes, we are starting the class.
Okay, thank you. Good morning. I guess you still have a morning right now. Everyone, nice to see you again here. I received your email about the last assignment. I will mail you back in a few days, if you don't mind. About deadline of a submission, someone requested to extend deadline. Deadline actually is the next week, not this week. So you have one more extra week for submission of first assignment, and for second assignment it's also 2 weeks. And don't hesitate to submit not finished completely assignments, because I will grade, as I said, I will grade not only the final result, but also the way how you try to get there. So if you didn't finish if you didn't complete a goal, didn't complete exercise, it doesn't matter. You may show how you tried to do it. But for some of you, it's actually can be maybe easy assignment, because I received interesting email from one of you who actually used CNN, convolutional neural networks, that we are going to discuss today. Yeah, we are not only going to focus only on convolutional neural networks, but also on object detection a bit. So yeah, so for some of you, some of information from today might be already familiar, or you might be already familiar with this. But I would like to start on a point where we stopped last week. Second. Okay, so last week we stopped here on neural networks. So we wrote a quite simple neural network that has only 2 layers, one hidden layer, one input layer, and one output layer. This neural network supposed to use for digit recognition, handwritten digits like this one. And some of you already finished the assignment that actually was to do the same procedure, but with your own handwritten digit. So you should write down the handwritten digit, load from your Google Colab, from the Google Drive, or some other way, and just to recognize it. So actually, as I mentioned on the last lecture, on the last class, during the last class, someone of you asked about the number of neurons. So this is, I just remind you, this is dense, it's a linear layer. Linear layer supposed to have this function as a main function, not activation function, but the main function, if you remember, this one, linear function, as I mentioned. In some cases, it might be not linear function for some neurons, but this is a dense neuron. So it means that this neuron should supposed to have linear function in this way. Second. So yeah, training is quite fast here, as you can see. Okay, and this is what we had done before. And the following thing is actually to this is just representation of images, nothing interesting. Yeah. So the few things that I want to discuss before we go into convolutional neural networks and object detection is training and validation and test datasets. So datasets should be splitted. Why it should be splitted? Also, during this part of the lecture, I will talk about overtraining. So how to determine the point where you should stop training your neural network, and the causes of overfitting. So how to actually prevent it. This is additional example of just datasets loading. So you can see here that from TensorFlow datasets, you can take directly these specific datasets. for example, NIST. You also can try to do the same in a Kaggle. So training, validation, and test data sets. So when you learn something, you usually you try to understand it, right? So you try to understand how it works. It provides the opportunity for you to do independent work or independent exercises with different data that you trained on. So if you trained to solve linear equation y equals 2x plus 5, for example, so when you understood how to solve this specific equation, you can do the same equation with different coefficients. So y equals 5x plus 10 and so on. But to do the same for neural networks is not a trivial task. So when you train on the same data, the neural network can show you pretty great results. So high accuracy, low loss, and so on. But to check if these results will be general for different data, for all data of this type, you should use data that wasn't used during the neural network training. So that's why you will get the test dataset. So when you trained your model, you will check how precise is your model on a test dataset. But besides of the test dataset, you also from the full dataset, you should also separate validation dataset. Validation dataset required for calculation of model precision during the training. So on each epoch, as you can see here, you get loss. But this loss is not representative, as I said, right? So during each epoch, you should select the model with best results on a test dataset, right? But we cannot use the test dataset because if we will use it, we cannot check a model. So leakage of information will happen. So to prevent it, you can just take part of your training data as a validation data. And you don't use this data as for training, but you use it for each epoch or for each set of epochs to confirm that what precision you're supposed to expect from this model on a test data set. And when you finish training, you already can train it, not train, but to test it on a test data set. Yeah. So usual ratio here, can be split it or like this one. So if you will have some data, you can split it. Be careful if you will have lack of examples. So if you have a lack of data, if you have not much data about some specific topic or where you're going to use your neural network, it's better to use actually machine learning, the regular one, not neural networks, like different trees solutions and so on. I will not talk about this one during these lectures, but you can check it. As I said, I put at the beginning of this notebook, I put links to useful resources. So yeah, and you can see here we can on this example of MNIST of handwritten digits, you can see that we actually have here the train, validation, amount of train, validation, and test dataset. So and test dataset equals around 16% in this case. So there is a few ways how to do it: manual splitting, use skill-learn model selection, train test split, for example. So you can create your own function that will split data. And for validation dataset, you can use only for validation, not for test. Test dataset, you can use these three versions. But for validation dataset, you can use model fit built-in function, that built-in and fit method of keras. library. So usually all of these libraries that I told you about, that like TensorFlow or PyTorch, they all have these built-in functions of validation dataset split. Be careful if you are going to use specific time dependent dataset. So if you will use a plot as training data, you should keep in mind that if you will split it in different pieces, and if you will shuffle your dataset, it will not be time raw anymore. So in this case, you should split in specific sets of data, and then shuffle. You can shuffle these sets. Depends on your task actually. Okay. I will not run it anyway. So this is example how to use how to do it by handwriting, like manual, without any additional functions. So you just do some cycles, you do some mask on array, you do some split all data set, and you can check that this data and this data will give us all total amount. So this is specifically roughly 16%, I would say. Train test split from Skylern library, also one of the examples, and self-created, for example, another one. Built-in function for valid validation dataset. You can see it here. This parameter is here, validation split. You can call it, and you will just put a parameter of percentage, how much you would like to use as a validation data. So all other persons, so 80% will go to validation data. So it means the test data you see xtrain here I used. So I first of all I split it xtrain and xval here. Yeah, this is a validation. So this is an example of validation splitting. But before you will do validation splitting, you should split test splitting. Same way as I said, but don't use this method here. But also, if you didn't use built-in validation data, you can also do this manually here. 1 second, I should do it like I'll fix it quite fast. Sorry. So here I split it manually without shifting with each other. And so, yep, it's from 0 to 56,000 elements will go to train data, and all other elements will go to validation data. So in this case, you can use a validation data parameter, not the validation split, but validation data. Validation split will split this set of data. But if you want to use specific separated validation, as I said, for time frames, for example, you can use this one as an example. Optimizer is one of the ways, it's built-in thing. I will not talk about this much right now, but it's extremely useful thing that actually includes different mechanisms of gradient boosting. 1 second, I will go here somewhere. Here should be gradient descent function. Yeah, here, as I said. So I already mentioned on the last lecture that for optimization of finding global minimum, there was built-in specific additional things. So it's not only count the gradient of this cost, not only count gradient of the loss, but also it counts the pulse. So if this, if we were here on the next epoch, we moved quite fast low part. So we should increase so-called our velocity or pulse or momentum of I would say our position. So it kind of usage of physics approach in this case, and it used to be helpful. You can do it by yourself, but as I said, I will not talk about this much. So in this case, you can use optimizer. Optimizer Adam, for example, of Keras is quite widespread optimizers, and you can check actually what other optimizers does it has, or TensorFlow does, what the optimizer do they have, and so on. So yep, there's a lot of them. In this case, in case of Adam, you can use like put a learning rate specifically here. So learning rate, I will remind you, this is like coefficient that will reduce or increase the learning speed, so the speed of changes of your weights. Yeah, and amount of neurons here is random, except the last one layer, because we have 10 classes. That's what it means. The optimization of amount of neurons is another story. You can do several models for specific tasks and choose a best model. And you can not fine-tune. Fine-tune is not for this case, the term, not for this case, but kind of tune your model by changing the amount of neurons. But in this case, you will need to train your neural network a lot of time. So yeah, there is a few rules, like quite obvious rules to put amount of neurons here. So if you will put amount of neurons below the value of how to say it, 1 second. So for example, in this case, 1 second. No, not here. We have 784 numbers, but the thing is that you cannot expect what features will neural network extract from these dimensions, right? In this case, but if we will get not for example pixels, if we will get I don't know, let's try. No, we will work with pixels. So I will explain. Sorry, it's a bit difficult topic. If we will reduce significantly here amount of neurons to 20, it means it's like this one. This is significantly lower than amount of input data. It means that we will get here a hidden layer, will get information loss, because some information channels, so some pixels will be joined, merged. If they merged, we will lose information, but not for this case. It's not so obvious, but for case, for example, house price prediction, you will get like description of house, the square, this how big it is, the square meters. You will get location of house, you will get I don't know, the amount of bathrooms and so on, year of building. So if you will get as an input layer 2 neurons, you will get lost information. So that's obvious rule. So you don't use 2 less neurons, too low value, because you will get loss of information, and then your model will not confine at the end of all. What does confining mean? It means that this model loss will get dropped. Sometimes it happens that you run training and your loss is not decreasing. That means that your model cannot confine. Okay. This is 3 epochs and example of accuracy on 3 epochs of this example of model. Just to remind you, we have here Muniz data, handwritten digits, and example of overfitting. Overfitting means that our model learned all trained data, but it cannot generalize the training features to general data, to validation, for example, data. If it cannot generalize on validation data, for test data, it will be even more terrible. So the loss will be even higher. So this is accuracy depending on epoch. So this is quite obvious plot that we reach some maximum, right? On this example, we have 100 epochs and we got some maximum, and even validation accuracy show us some maximum, right? We cannot see any specific features of this plot, but here is definitely overtraining or overfitting of model. How to determine it? You should build plot not of accuracy, but plot of loss. When you build plot of loss, you will see that training loss will go down, right? But validation loss, as you can see, it goes down till some point and then it goes up. So it means that you will, this is definitely a feature of overtraining. If you see this pattern, definitely you have overtraining. So that's why it's important to analyze the output plots of models. Yeah, sometimes there is so-called callbacks. You can learn about this one on Keras main page, for example. Callbacks is built-in in model methods that will stop training after the increasing started. So it will determine minima, extremum of this plot, and will stop training here. So the optimal position for validation data. Yeah, and so don't try to get training loss significantly low. Try to get validation loss significantly low, but they should be same value, roughly, not extremely same, but close to each other. But if validation loss lower than training loss, it means that something went wrong. You should rewrite your neural network. 1 second. We'll pass. Going further. Yeah, this is bit causes of overfitting. I already told you that why it is important to have test data set, but also I told you about that if you have too low amount of neurons, so your model will not confine. But also, if you have too complicated model structure, it can cause overfitting. So you should keep a balance of it. That's why usually when people train models, they train not one specific model that they wrote, but they run cycle of trainings. That's why they use a lot of GPUs and so on, so to perform it much faster. Yeah, but also it can be caused by small data set, bad quality of data set, because sometimes data set labels can be just wrong. It definitely, for example, of digit, definitely 9, and the label call it 3. It happens because it's data collected from people. So you have some natural percentage of data set mistakes and errors. What else can be? this balance of data set. What does it mean? It means, for example, in our case, if we will get from 60,000 images, we will get 40,000 images of digit 3 and 10,000 images of digit 5, and only 10 other thousands will be for all other digits. It means that our data set is not balanced. We need roughly equal amount of image of each class that we would like to determine. Yeah, so this is depends on balance of data set. In this case, you should just balance it. For example, you will get less data, but you will get a balanced data set. Check if this data is enough for you or not, and just try it. And the fifth reason is too much epochs of trainings. So even for best model, for balanced data set, and for big enough data set, if you will train long enough, you will get overtraining. You just need to train long enough. So that's example. What happens here? That's a bit detailed information about this one, because I tried to write this notebook that you can use outside of the class, not so without actually checking a lecture. So I tried to put here as much details as possible. So possible ways of solutions: extend data set, obviously, right, or cleaning it, roll back to the simplest possible architecture. Also obvious, right? So we can reduce the amount of neurons, we can reduce the amount of layers, and so on. And this third one is interesting thing that actually used a lot of times and help to confine the model better in many famous architectures. Like we will talk about one famous architecture that increases object detection to like another level. We will not talk about this most modern one, but I will talk about this one of the famous. They used dropout and batch normalization layers. We will talk about this a bit later. Rebalance data set, obviously, right? Tracking of metrics. So in case of you're worried that you are putting too much epochs, you can stop your training using callbacks. Here is a link to callbacks. You can use callbacks called checkpoint, model checkpoint, or other callbacks. So it's possible. And you also actually, you can use your own handwritten callback too. So you can combine several callbacks. So for example, your callback will save model with a minimum validation loss value. So you can continue training, but the best model will be saved already. So all other models will not be saved. But you will just spend your time while you train models that are not better than the best one, right? Because you need only the best one model usually. So in this case, you just stop training. So early stop. So if you get on a plateau, like on some specific region where your validation loss is not dropping down, you can stop your training. That's all. Yeah. So please check this callbacks. This extremely useful like instrument. Dropout layer, as I mentioned, we will talk about this too, guys, and we will follow to convolutional neural networks. Sorry for so long talking about this one. In normal state of dense layer, all neurons connected to each other. So the first neuron here connected to 3 neurons of hidden layer for all 3 neurons. The second neuron also connected to all of 3 of them. But what does dropout layer do? Dropout layer turn off randomly several neurons. So it can turn off, like for example, this neuron and this neuron. It means these two channels of information will not go anywhere. the other possibility, that's one of the examples. So dropout randomly turn off neurons. It can be a central neuron or this first neuron or something like this. You will put as a argument only the percentage, the percentage of turning off neurons. I will talk about this. So here, if we will put the layer, we don't, the dropout layer doesn't has activation function as an argument. You don't need to clarify it here. So 0.3 means that 30% of neuron of this layer, dropout layer, will be turned off. It means that information from them, output of these neurons, will not go further to other neurons. I guess it's quite obvious, right? So let's see an example of using dropout. Here, 20% of neurons, as we can see here, is the 50 epochs, right? So in our case, we should see that our overtraining should go lower, right? So here we can see that it's not extremely good, but we can see definitely that overtraining comparing to this one is significantly less, right? So because this is around 7% raise for 100 neuron epochs, right? Like, so somewhere here. Oh, not 7, but it's 5% raise, and here is less than 5. That's 2% for 50 epochs, right? So this is accuracy, this is loss, but the thing is that sometimes dropout can actually prolongate. So you will need more epochs to confine to model for model to confine. So you should use more epochs to confine model. Don't put too high value for dropout. It also will be bad. So in this case, in a biological sense, a biological analogy, it means that when we try to train to something, right, our brain trying to remember everything about this one. So if we will, our like few neurons of our brain will die, all other neurons will take it to work. So it means that like this neural network can do some general conclusions, general feature extractions. It helps a lot. Yep. Going forward, batch normalization. No, it's applying only. I see the chat. I'll check the questions. It's applied only during the training. During the testing, you already have fixed position of neuron and fixed weights of each neuron. So it's already fixed, except you have reinforcement learning. I will not talk about reinforcement learning, but I mentioned it once. Reinforcement learning, it's when the model doesn't have data set, labeled data set. So, for example, you try to teach your model to play some video game, but you just cannot build a data set. Well, you can try, but if you don't have one, what to do in this case? You just teach your model on its own games. So the most important thing in this case that you develop the cost function. So you will develop that, oh, this was a bad behavior, then we will reduce your score. If it was good behavior, we will increase your score. So model try to optimize itself to find a maximum score and build its own data set. There's a few advantages of reinforcement learning, but I would say the most problematic part is its development. So these models that I'm talking about, it's easy to develop. You can see it, right? So the process is quite straightforward. But in case of reinforcement learning, you need to think seriously about how can you define the cost function. The cost function is the most important part of reinforcement learning usually. So how can you estimate grades of your neural networks? So it's the same as with a student. I will estimate your grades. I have a system, but what if I haven't system, right? So what if I haven't? I need to develop it. So that's can be problematic. Okay, going forward. Did I answer your question about dropout during training? Okay. Batch normalization, it means when you have sometimes not disbalanced data, but data with huge fluctuation of values. It means that sometimes you have prices of houses that can happen. Your labels, for example, or not labels, but square feet of square meters of houses area can differ from one to another, and it can be problematic because the difference between them can be huge. And in a one batch of data, part of data, you can apply like all extremely expensive houses, and the second batch it will be cheap houses. So it can possibly happen. So in this case, model on a one epoch will train one way. On the second epoch, it will reduce weights in another direction. So to prevent it, actually, you can apply batch normalization. So if you apply some batch of data in model, you will normalize current set of data, only current. You will not normalize all data, but you will normalize current set of data. Well, actually, it's not only for this case that I described before for house prices, but also it can be happens if you have complex architecture of neural network. You will get sometimes numbers that are quite high. So you will in between layers there are possibilities that some fluctuations of spikes, for example, and these spikes. And sometimes it can be useful, but not in a general case. So if you have specific spikes of data, your data, for example, not normalized well or something like this, it can be happens, or it contains some errors, you can use batch normalization. So in the middle layer. Batch normalization by itself, it's not used and drop out, obviously. Better not to use them as an input layer. Dropout definitely don't use, because then you will turn off input channels. There are barely few cases when you can apply. I can imagine when you can apply dropout as an input layer, but don't do it. Yeah, don't do it. Batch normalization, don't do it, because you already when you build your pipeline before you start training of neural network, you remember you should normalize data by yourself. The whole data that you contain, take. Well, except only one thing that I didn't mention, that sometimes it's better to normalize train data separately from test data. It means that train data will has own normalization and test data will has own normalization. So we don't know max value for X test data. Well, it obviously will be up to 255, but in case if it will be 256. So to prevent this separation of normalization required for prevention of information leakage to neural network from test data set. And also that's in principle, in theory, every time then when you test your neural network, you have information leakage. In principle, in theory. But obviously, Usually you don't care about this one. Okay, going forward, I put normalization, batch normalization here. Where's batch size here? Batch size here 256. It means for each part of epoch, for each set of epoch, not set of epochs, but for how to explain it. Okay, I will explain it other way. Batch sizes means that we will have the whole 60,000 images. We cannot, sometimes we cannot put it in our RAM because our random access memory is limited. So we should split it in separate chunks. So we will split it in separate chunks. This chunk will model will be trained on this chunk. So it will calculate gradient for this chunk, the full gradient. Then it will update weights. Then it will go to the next chunk of data, also 256. And the end of all, if you will not get to the last part of the full data set, can be not equals to batch size, so all leftovers will go to the last chunk. So don't worry about this one. And as you can see, so 211, it means that we have so much chunks of 256 images. So much chunks. Is it understandable? What does batch normalization, no, not batch normalization, batch size do? Okay. And yeah, but batch normalization, as I mentioned, it normalized data like in the middle of training. It normalized batches. So these 256 images will be normalized for its own maximum and minimum. It means that sometimes some images can contain maximum value below this value. And yeah. So yeah, it will be changed using the batch normalization. Or it will be gray image, for example. So it means that it will not contain 0. Also happens. And after batch normalization, you can see we still have some overtraining on upload, some overfitting. Evaluation give us 98%. Meanwhile, after dropout, we have also similar value. And before everything else, we also got similar value. And we can combine these two methods, actually. If we will combine them, we can put batch normalization, dropout together, and then we can get also 50 epochs, same parameters. We will get also the same result. This case, this specific case of MNIST images has own limits. So batch normalization and dropout didn't help it here. So be prepared that sometimes you will try to use batch normalization and dropout, but it will not help in some cases. Yeah. Personally, I don't know in which cases it can not work, but yeah, if you see overfitting, just try to improve it using batch normalization and dropout, especially if you have so simple neural network as this one. But yeah, sometimes it cannot help. Going next topic of my talk today, convolutional neural networks. I will try to go faster. Yeah, so convolutional neural networks is a neural networks that actually will work a bit more similar than our eye. So in previous example, we tried to solve the visual task using the digits and neuron model, but convolutional neural networks will work more like our eyes. It specific layer in case of neural network that will do this operation. What does it do? So when we see something, when we try to see something on the image, not only on an image in a real life. When we see apple, we can observe something around apple, but a focus of our sight usually at one point. Well, sometimes people can move their eyes separately. They will have separated focus, but in this case, it will not be kind of stereo vision. It will be like how it called? I forgot how it called, but it will not be stereo vision. It will be other type of vision. So yeah, in a common conditions, people have only one focus point for both eyes. But you can still have opportunity to see the surrounding media of this focus, right? So you can see apple, but if something will fly around apple or even far away from apple, you will see it, you will mention it. But to see better what exactly flying, you need to shift your focus, right? Same actually mechanism laid down below convolutional neural networks, and it also can relieve linear layers, linear dense layers, because linear dense layers are quite resourceable. So you had to spend a lot of resources on it sometimes, and you will get a lot of big matrix for operation. It's not extremely useful sometimes. So this is an example. Dense layer, the amount of weights for 320 by 320 pixels by 3 color channels image. We will get 307,020 weights. It's not neurons, it's weights, the parameters that I told you about. Remember where it was? These parameters. This is W weights, just to remind you. But what happens with the convolutional networks? They convert the squeeze image. So convolutional neural network or convolutional neuron determined by kernel size and a filter size. What does filter and kernel size means? It means that our kernel, for example, is size of vision. So this is kernel 3 by 3, for example, here. And filter here is a medium size, so amount of our neurons. Few advantages of it. This image may be not understandable for you right now. Yeah, but I have here other examples. I will talk about this one a bit more. So the few advantages: local perception. It means that specifically on images, convolutional neural networks can determine localized feature. It means it will try to find features in specific location. Not all features of this image, but it will also determine a localization of feature. It has shared weights, dimension reduction. Dimension reduction, it means that after your convolutional neural network, you will get lower quality of image, but for classification task, for example, it's not problem. This lower quality of image will reduce loading on your GPU. So you don't need this much parameters. Amount of parameters will be reduced. So for example, here, 3 by 3. So this is a matrix 5 by 5 input layer. Filter or kernel size, this kernel itself has dimension 3 by 3. It means that it will go for each step. It will try to go initially this window. So 0, 3, 0, 0, 1, 1, 4, 0, 5 on the first step. And we'll try to find sum of its weights. So for example, 3 multiplied by 1 plus 0 multiplied by 1 plus 4 multiplied by 1. We will get 7. Next step, window step. 301.111.052. Same operation, we will get 1. And then third window, 012.110.521. Same operation, we will get 8. And so on. No, next row, so we will shift our window below on the one row, and we will go for each column shifting. We will get some image. Where does CNNs used? Classification, segmentation, and it also used in object detection. I will show you at the end of today's lecture. I will show you the YOLO architecture. It's quite complex architecture. You definitely should play with it. It's really funny thing to work with, especially new model. I will show you old one, but you can check on the internet which the last version of YOLO model. YOLO, it's rephrased. You look only once. Never mind right now. So conv layers can be used with max pooling layers. Max pooling layers also has some kernel size, so pool size, so-called. Stride, it means it will step. So in previous example, I show you step one by one. So we shift it on one row or one column. But in case of the max pooling, for example, or even in case of actually convolutional layer, you can adjust your step. So you can do step, for example, size of window. So you will not overlap your previous window. It sometimes can be useful. Max pooling layer extract maximum value from windows that it try to observe. So it can pull out the most important feature from the neuron. Sometimes it can be useful. So it help to separate each neuron. So separate duplication of neuron feature detection. So when one neuron works fine and try to find some features, and the second neuron does the same, it's not very good for us, right? So here is where max pooling, for example, it's not the best case, not the best example maybe, but it can help us. And also, it also reduces the size and dimensions of data. So you will use lower dimensional matrices. And multiplication of these matrices will require less resources from you. You also has the argument is a padding argument. Padding argument is useful when you don't want to reduce dimension of data. Sometimes it can be useful. Like sometimes you don't need to reduce dimensions of data. In this case, you virtually expand your input layer by zeros, for example, or maybe not zeros. Sometimes you can use other values. You can expand it by zeros in this example, and then after filter, you will get feature map same size as an original input layer. To do this, you can do padding argument same here as an example. So this is an conv2D. It's a convolutional layer. This is amount of filters or neurons, convolutional neurons. This is amount of how much neurons do you have, and this is your actually pool size or filter. Why it has two parameters? Can someone tell me? Do someone has ideas why our filter size has two parameters? Just in case. Wrong answers are acceptable, please. No one. You can answer in the chat too. I'm reading your chat. Why we have 2 digits here, not 1? Any ideas? You can use micro if you want to. No one. Okay. I will not try to ask you much today. Then it's because we have two-dimensional data. So conv2d convolutional. Yes, that's true. Thank you, Sonia. That's correct answer for column and row. But the funny story that actually we have in Keras library has also convolutional layer for one-dimensional data and for three-dimensional data. So yeah, these 2 dimensions. That's true. That's quite simple question. If you don't want 1 second, I will do this. If you don't want to do this process on image, so if you don't want to have same size of output data and input data, you can use valid as a parameter. So same and valid. That's true. That's two options that you got. But you also can check the other arguments of conv2d layer in Keras library documentation. As I said, all other libraries like TensorFlow and PyTorch, they also have these layers. So this is a quite famous layer. They're all quite old. I'm sorry, we are running out of time. If you don't mind, I will take another 20 minutes. Is everyone okay with it? Okay. Thank you. Sorry for delaying, because we are supposed to go faster, but yeah. So this is image classification task. As I said, the same, similar to previously mentioned, but not with digits. Now it is 20 classes, as far as I remember. No, 10 classes, but not digits. It's now objects. So frog, dog, horse, cat, or something like this, like bot, plane, airplane, car, bird, cat, deer, dog, or deer, sorry, frog, horse, sheep, and truck. This is 10 classes, different classes. It's a bit more complex task because here we already have not only black and white colors. We have 3 channels, 3-dimensional channels. So that's why we should use actually our convolutional layers, because we should squeeze amount of parameters, so reduce loading on our GPUs. I will run it right now. Okay, 1 second. Yep. Now, as you can see, I put here random images, so we can see different horses, cats, and so on. So batch size will be 256, for example. The biggest amount of neurons will be at the input. Here I declared input shape. Input shape here is a 32 by 32 pixels by 3. So we have all 3 channels. We don't flatten. We don't need to have flat data, as it was in the case of linear layer, dense layer. 64 neurons on a second layer, on a hidden layer, max pooling. Then we will flatten it we will make our data flat because we need to solve classification, because we need output as a 1 digit. So we will at some point we will need to do this flatten operation. Then it will be dense layer, small dense layer, dropout, and output layer with 10 classes neurons. It will be categorical cross entropy because it's suitable for this case loss. You can read about this one a bit more. Losses is interesting thing for deep learning, and depending on the task, you should choose best loss for your task, most suitable, because it will be, for example, binary cross entropy will not fit here well, and mean absolute error, for example, too, because you're not trying to predict some value. You don't care if it so the mean absolute error will be wrong here, completely wrong, because if it will be tracked if it will be tracked and you predicted, for example, car, so the difference between these two will be 9. No, not 9. Yeah, 9. So no, sorry. Then 8. It's quite big at almost maximum value, right? But technically, we don't. It doesn't represent what we are trying to do. Much better to have probabilities here for each object, as we done before. Probabilities for digits, but here probabilities of each object and each class. Sorry, each class. We don't predict here object detection. We don't detect objects on a complex image. We only try to do classification task. So yeah, it doesn't represent. That's why we used categorical cross entropy. There is a lot of built-in losses in Keras, TensorFlow, and PyTorch, but also you can use your own written losses. But before you going to write down your own loss, just check for which specific library do you write it. And the second one, check it if it works well. And the rules of library. So the rules of how to write losses completely. So you will definitely get labels, you will get input data, how to calculate it, how to normalize it, predict it, and so on. And we will go our training validation split, as you can see, we've done here 20 epochs. Batch size will be 256, as I said. X-train 10 is our okay. Here we have categorical cross entropy. Yep. So X-train 10 is original data. Y-train is the labels that were converted to categorical one-hot encoding method. You remember one-hot encoding? It means that we will have here probability of each class. So we will get, for example, this will be first image. So we will get here 1, and all others will be 0. For next image, for second image, we will get here 1, here 0, here 0, and so on. So just to remind you, model fit we will do. It will be quite fast, not so fast, but we will do prediction. And we will try to. The first epoch usually takes a bit longer time. You can see our accuracy quite low at the beginning, and loss is also quite high. But you can see on the second epochs, it's already twice. The accuracy already twice. Loss dropped significantly. We will wait for a bit to finish it. Yeah, so this an example Yeah. This is also a classification task. So we will leave it to train. We will leave model to train. So this will be a result. And the next set of tasks for neural networks is image segmentation. So you should calculate area and position of area specific like areas of images. How does it work? 1 second. So for example, here we have images of fishes. It can be useful for fish tank, for example, for fish ship. I don't know. And we can we need to calculate where exactly our fish and where it is not fish. So where exactly is the table. So we definitely will get some, and we will get as a labels these images. These images is the correct answers for us. Is it finished the work? No, it's not finished, but we already can see that we have almost 80% accuracy. That's nice. For this case, binary cross entropy for case of the image segmentation, usually used binary cross entropy as a loss, or categorical cross entropy, also possible. Just that this coefficient is coefficient of twice interception of areas divided by areas sum. And Jaccard coefficient, this formula is here also. We will wait for a few seconds more. We will see the result. I'm also curious when it will end up. 90%, not bad, right? For 10 categories of different items for this simple neural network, that few rows only. You never mind. You can also turn off this visualization here by putting here at 0. So we can got here correct answers, right? But this is accuracy. We should do the same, but with loss. Let's do it. And we can see that we will get our overfitting somewhere after 4th epoch. So, and our not percentage of correct answers, this is a loss. So percentage of correct answers around 50%. It's not very bad, especially when you consider that it tried to choose between 10 categories. So randomly, it will be 0.1, it will be 10% correct answers. It's randomly. If we will get 10%, it means that our model is useless, completely useless. It's just random. But we have 50. It's quite nice. And we will try to predict model output, predicted answer 4, correct answer 3. It predicted that it was deer. Doesn't look like a deer, but yeah. Never mind then. Going back to image segmentation. So yeah, I have links here for segmentation titles and so on, and for if I'm using some specific layers or information from the articles, I put links here, so you can check it. By the way, we will get several layers here. So 1 second. So dense layer you already know, const 2D layer you already know. Will it work? No, no. Fine. Can it done this one? Doesn't want. I just want to show it on one screen. One screen. So here, you already know convolutional layer, max pooling, flatten, dropout, batch normalization. Few new layers concatenate. It's a layer that combine to matrix, can combine two matrices into one, for example. Activation layer. Activation layer we will need when we need to clarify activation function after several layers, for example. It can be happens. It can happen that you applied activation function as separate layer. Input layer, yeah, I think it's obvious from the name of it. You just use it for input. It not. I will show you where to use it, because before we used sequential. You remember that for all our models we use sequential, but also I will show you today that models can have not one input. So for example, in case of houses prices prediction, you can use not only description of houses. Description of houses is text-based information, but also you can use images. Images already, you need to process images using convolutional neural networks. If you are using convolutional neural networks, you usually don't use convolutional neural networks with 2D, especially conv layers with one-dimensional data. That it is text-based data. So what to do? In this case, I will show you how to work with. Few utils, pyplot for visualization, numpy, that we will need to store our arrays, pre-processing for image visualization, another PIL below for images, trying to split, as I mentioned before, backend cares, I will talk about this one, and interesting thing, the data generator. Okay. I will load fish data set that this, where it is, this data set. I will loading it. It will take some time. And also we'll need to load segmented labels. So labels of for these fishes. So these images I need to also load. These labels are also images. So we don't have here categories. We don't have here numbers. We don't have here cat, dog, or something like this. No, we need to determine coordinates of our fish. That's what we are trying to achieve. Well, it takes some time. So this is, you can read what it happens here. I try to do it as obvious as possible, but if you will have some issues, just let me know. So this is just to convert colors, for example, to indices, because you remember that our neural networks don't work with colors, it works with digits. So in case of this two colored images, of segmented images, we need to put not number of white color, but Someone leaving, okay. Okay, not white color number, not white color value, not 255. We need to clarify what index does this image has. So technically, we have two indexes here because we try to segment image with only one object. So everything that not this object will have index named 0, and everything that has object will have index 1. That's why this happens here. So everything that not object. So if we will have some color here, we will get index 1. We should do function that converts our indices images backwards to color images. So we will get here specific color for fish if our index. Some support function for segmented images, preparation for categorical cross entropy, categorical one hot encoding preparation, and so on. Trend test split. So did it load? Yeah, it takes quite a long time to load. Okay. We have 1000 images. It takes some time here. Validation split. And here I used K background as to actually write down dice coefficient function that actually will be our loss today. So we here wrote down handwritten, our handmade loss. This is not included in Keras dice coefficient. And there is several famous architectures that can be used, like PSP.NET, for example. Do I have others? No, I don't think that I put other. No, I didn't put here other architectures, but here is an example of PSP.NET that contain, for example, 3 channels, 3 big channels, so 3 branches, as you can see. So the first input image goes to one specific layer. So yeah, we don't care about this one right now. This will be our architecture today, but it's not limited by this, but by the way. So separated by three, I would say, windows. So this window 128 by 128, window 64 by 64, and window 32 by 32. So this window will try to find big objects or what? 1 second. Yep. So this image will this branch will try to find big areas. This branch will try to find smaller areas, medium size, and this will try to find the borders of our fish. So small parts, small pixels. And then together we'll concatenate these 3 output images, and we will push it as a some output image. I should emphasize that we have in this neural network have output as an image and input also is an image, because before we worked with images in images as an arrays here. As an array. So we have 2-dimensional array, technically 3-dimensional array, because we have also color channel, and this is output also will be x-dimensional array. In our case, it will be 2-dimensional array, but in some cases it can be several dimensions of array. So 20 depends on how much classes do we have. Here we have only 2 classes, but we can segment image for many other classes. Why we care about image segmentation? Because it used to be a first step of object detection. When we try to find some object on the image, when we try to do some computer vision, not trying to chase only colors, because when you try to find a chameleon on an image, chameleon can change its color, right? And your color filters will not work anymore. So segmentation, quite useful. Is it almost quite useful, or used to be quite useful, and there is a lot of architectures that can be used, and we will use only this PSP net today. You can use also UNet, for example, architectures and so on, but I don't think that segmentation is not extremely interesting as maybe for you at the beginning will be. But yeah, as a training, you should try. You should try. The most interesting part will be right after this. It will be soon, the most interesting part of today's class. Sorry that I'm delayed so much. Come on, faster, please. Okay. This I will not stuck on it. I will just tell that we have here everything that I mentioned here. Well, except we have additionally here batch normalization, but it's not a big deal, I guess so, for you. Yeah, and one other thing. You remember that we declared input is on layer. Here, you can see we used this input layer, input shape. So this is not sequential model of neural network. It's not sequential, I should mention to you. So we used here, you can see how it works here, like how different it from the sequential. We don't use model.add anymore. Not well, you can use it definitely, but here you can have different branches, and model.add will not allow you to have separate branches. Model.add only suitable for straightforward architecture. That's important. But here we have some branches. These branches is not possible to use with a sequential model. So you can use, we have some block 1, block 2, block 3, and we have output of these 3 blocks, block 1, block 2, block 1, block 2, block 3 output. We can concatenate them together. They should be the same size. Important mention to mention it. And we will get some output as an image, number of classes with same padding. And here, how you compile this model. So in case of sequential, you declare model object before you start building your architecture. In case of model class of neural networks, you declare it after you already prepared your architecture. So you first of all, you declare some architecture, then you will say this will be my model. You will put here image input, and image output will be output of my model. You can do like this. You can have separate inputs, for example. And so on, and separate outputs, but not in this case. So don't worry much. Compilation is the same. Metrics, sorry, not loss. Here we used metrics. We handwritten our own metrics for our model to calculate how good is our model. So we compile. But here, as you can see, this is a function to build the model. So here, this is all function. So here I'm running the function. I will try to train my model. You can see it's training and so on. Training is quite fast, as you can see in my case. Validation dice coefficient goes low. You can see that we got here some overtraining, or not maybe much. Here's the 5 examples of 2 classes. Ah, no. We didn't have overtraining right now. Nice. 5 examples. As you can see, our model works fine. We can segment the fishes in this example. Yep. I saw raised hands. What question do you have? No question? Okay, that means it's no question. I don't. By the way, I don't hear you right now. So if you want to say something, just unmute yourself. Your microphones by default are muted. So here's an example of segmented output, but we didn't use here. Okay, we didn't use here white color. I used here a red color because I would like to actually put one color on the top of this image. So we can see that a bit error about tails, but in general it's quite nice, right? So I will be fast right now. So it is introduction to object detection. I will skip this part. I will talk about YOLO architecture straightforward. YOLO architecture is architecture that tries to draw boxes around objects. So we will get as an output 3 sets of data. So coordinates, class of object, and probability of object. It means that first of all, we need to clarify that we have some object, maybe it's car, maybe it's human, maybe it's cat, never mind. So we should clarify what object do we have. Then we should clarify how precisely are we sure that we have this object. And then we should clarify where it is object, on which borders. So in this case, this complex YOLO V3, it's V3 right now. As far as I remember, right now it's YOLO V12 already exists. So this is a quite old YOLO model, but it was game changer at 10 years ago, I guess. It was game changer for YOLO architecture. YOLO architecture was game changer for object detection. How it works? So it have straightforward like residual block, some convolutional layers and so on, but it has 3 main branches. One branch has 52 by 52 spots. Second branch has 26 by 26, and third branch has 13 by 13. What does it mean? It means this model, well, you can imagine this model before it started training on any image, virtually split each image on 3 separate grids. First grid, 13 by 13. It's a grid to find big objects. Second grid, 26 by 26. It's a grid to find middle-sized objects. And 52 by 52 grid to find big, small size objects. So this is how it works. So usually for each of these branches, you will get probability, you will get class, and you will get borders of this class. So the size of this class bounding box. So the box that's surrounding the object. Each of these branches has it, but the thing is that you should separate all from these all branches the best results of prediction. It means that for each case, your model try to predict 3 times. Yeah, it actually released a lot comparing to previous models. I will not talk about this one. This model architecture with 3 branches already separated our images on some grid, already relieved the task of image detection significantly. So YOLO v3 is first model that achieved real-time object detection. So it means on a video. Not extremely good, though, but later versions actually quite good. Can I find and open? What happens? This works. 1 second, I will check my data. Okay. Okay. I will not talk much about this one. If you're interested in object detection, please take your time. You can check how does it work, what happens here. You can read, as I said, also Hugging Face resource that I told you about on the last class. All links are in the notebooks, in my notebooks. Hugging Face is an open source resource, so you can go there for free. So here's a bit tricky because I followed this actually architecture. So I created res blocks. Res block is contained 0 padding and conv BL. So convolutional batch normalization layer. Convolutional batch normalization layer. This looks like this. 𝗬𝘁𝗂𝗿𝗀 here is the activation function. Yeah. The only thing that I don't show here that training process of YOLO model, because training process takes some time for object detection. I will just lower the weights, but technically training is the same as for previous models. Don't worry, for assignment, I will not ask you to work with the YOLO model. It's optional, completely optional. If you want to, it will be nice. I think it will be more interesting for you than for me to check your YOLO models. So this is just a function to normalize. The only thing that, not to normalize, to visualize our data, output data. Here I have YOLO prediction results, as you can see. So nothing really interesting here. Okay, here, as you can see, for our plane, we have 3 boxes, you see. 3 boxes that show us where is our plane on this image. This is output of our neural network. Box, not box, because to draw this box, I need to use this code here. So you will have only class, so list of 6 parameters, as far as I remember. 6 parameters, class, probability, xy of first point, and xy of the last point. So 2 diagonal dots of our rectangle. Okay. And now we should choose the best bounding box. The best bounding box is a bounded box where a probability of our plane is the highest. So we just should compare it. That's all. It's easy. And yep, you can see we found quite nice bounding box. Even though some bounding boxes you see doesn't count the nose of of our plane or some part of wings, the best bounding box, as you can see, works quite nice. Training process how to train YOLO models by yourself, you can find on Hugging Face. But if you will have some questions, feel free to message me. As I said, I will try to answer on your assignments questions that you sent to me as soon as possible. As I said, in a few days. That's all for now. So please use YOLO models, use segmentation or something like this. Enjoy your machine learning and neural network development. Do you have some questions? Let's roll up. No questions. Any? Okay, never mind then. Thank you for coming here today. Sorry that I had delay today again, but otherwise I had to leave this YOLO and you will not see it, and it is quite funny model. No. Thank you for coming here.